Today we are going to discuss our statically indeterminate structure. So before entering into this chapter, it is important that you know what is indeterminate structure. So it may be recalled from your classes of strength of materials and statics that structure or one of its member is in equilibrium when it maintains a balance of force and moment, right? In general, it requires that force and moment equation of equilibrium be satisfied along it three independent axes, meaning all the forces in x direction must be 0, all the forces in y direction must be 0, all the forces in z direction must be 0. Same way, all the moments in x as well as y and z direction must be 0. So total 3 force equation and 3 moment equations. So total 6 equations are there, which are known as equations of equilibrium. Now in principle, in the most structures, the main load comes in a plane, or these loads are known as coplanar loads or coplanar forces. So the main requirement of 6 equations of equilibrium reduces to only 3 equations of equilibrium, because we are dealing with only coplanar forces. So all the forces in, let's say, in x direction, all the forces in y direction must be 0, as well as the moment for particular with respect to some point must be 0, but it must be in the xy plane. So we can say that equilibrium equations provide a necessary as well as sufficient conditions for equilibrium. When all the forces in a structure can be determined strictly from these equations, the structure is known as statically determinate. You are using all the equations to solve your reaction forces. Structures, if it has more than available the reaction, it has unknown forces or reactions more than the available equilibrium equations, then this type of structures are known as statically indeterminate. So when all the forces in the structure can be determined from these 3 equilibrium equations, then the structure is referred to as statically determinate. And if the reaction force or the unknown force is more than your already available equilibrium equation, like 3 equations, so then those structures are known as statically indeterminate. So let's say for a coplanar structure, there are obviously maximum 3 equilibrium equations, but for each part. So if the structures are having 9n parts, then there will be a 3n equilibrium equations. And now say there are unknown forces are r. If this unknown r and your equilibrium equations are 3n are equal, then you can calculate all the r forces from this 3n number of equilibrium equations. But if r, the reaction forces, are more than your available 3n equilibrium equations, then you can't determine all the reaction force. That's why it is statically indeterminate. So that's why it is indeterminate, because you can't determine. So that's when you can't determine all the reaction force, that is known as statically indeterminate structure. So that is the basic idea of statically indeterminate structure. So why these kind of structures are more advantageous over single span simply supported beams? So some benefits are like the bending moments are generally more evenly distributed, between the center of span and supports of members while it is a continuous member. Also, the size get reduced due to if you are using a continuous member. Also, in the case of frame structures, if it is there is a continuity of members, it leads to a much more stable structure. It leads to increase the stability of the structure. And if it is a continuous post-tension girders, let's say, then curved cables can be suitably positioned to resist the span and support moments. And also in another thing, the deflection are comparatively small as compared to the generally just simply supported spans. So you can say there are different more advantages if you are using a continuous indeterminate beam or structure in general. So when an indeterminate structure is pre-stressed, redundant reaction will develop because there is already at the suppose there will be restraint while you are using pre-stressing, while you are pre-stressing the structure, so it will try to deflect in and try to deflect at the supports, but the restraint at the supports will resist it, and that's why there will be some redundancy in the beam or in the structure itself. While a statically indeterminate structure is free to deform when pre-stressed, if it is a statically determinate structure, it is free to deform. But if it is continuous structure and it is indeterminate, then it cannot deform freely, right? So redundant reaction will develop as a consequence of pre-stressing, and this reaction will result in secondary moments. So if let's say you think a two span beam is there and you are pre-stressing at a eccentricity below neutral axis. Now what will happen? It will try to deflect it at the middle upward, right? But at the middle support, because of the support, this deflection, the beam is trying to deflect upward, but there is a support at the middle, so that support will resist it, and this resistance, this strength will create a new reaction that is known as the redundant reaction. And as you are restraining it and there is a reaction, so automatically there will be a moment. So this moment at that support portion is known as secondary moment other than primary moment. And what is primary moment? What we are meaning by primary moment? So primary moment is the apparent bending moment at a section in a statically indeterminate structures due to actual eccentricity of the tendons from the centroidal axis. So due to the eccentricity there will be apparent bending moment. So that is known as primary moment. But the secondary moments is what? It is the additional moments induced at a section of a statically indeterminate structures due to the redundant reactions, and it is developed as a consequence of pre-stressing the structure. So that is the difference. One is the general moment that due to actual eccentricity of the tendon it will develop throughout the beam, and the secondary moment due to the redundant reaction at some supports where it will try to restrain the pre-stressing of the structure. There this type of reaction will generate, and this will create a secondary moment. And as a whole, at a section of indeterminate PSC structure, we will get the resultant moment. So resultant moment is the sum of primary as well as the secondary moment is giving the resultant moment. So you have your primary moment, and due to redundant reaction there will be secondary moment. So and the sum of this both moment will create the resultant moment in the whole structure. Right. But there are some disadvantages as well while you are using a continuous pre-stress concrete structure. Especially there will be loss if because you are using a long cables throughout the whole structure. So especially due to the friction, as you already know, you have already studied, I think, in the loss of free stress due to friction. As you are going from one end to other, this loss is getting bigger and bigger. So if it is a continuous and long beam, so this loss of free stress will be much more. And also because of creep, shrinkage and temperature and other stresses will induce very high stress unless they are obviously controlled or provided for in the design. If you are not providing this in the design, then creep, shrinkage and temperature and settlements of support may induce quite a high stress. Now, cables positioned to cater for secondary moments are not generally suitable to provide the required ultimate moment under a given system of loads. That is also a disadvantage. Also, the computation of ultimate load is generally influenced by the degree of redistribution of moments. So this a disadvantage can be tackled or catered, from loss of pre-stress due to friction. That also can be tackled. How? If you reduce the curvature of the cable, that also can be done. Also, you can suitably select the profile of the tendon so that it do not induce any secondary moments. So your placement of the cable in such a way, you are placing the cable in such a way that it will not induce any secondary moment. And this type of tendon profile or cable profile is known as concordant profile. You are using profile through the line of thrust or the pressure line, so automatically whatever the moments are coming, your profile is cable profile is placed in such a way that there will be no redundant reaction, and so there will be no secondary moments. So this type of profile is known as concordant profile. So while you are using throughout a tendon, so it is important that you achieve the continuity. And how it can be achieved? So by using generally curved or straight cables for several span of the beam, you are using curved and straight cables. So also it can be used that you using for a single span one profile, one tendon, and for other also you are using another cable, and then these two beam you are attaching with a cape cable. Or alternatively, short straight tendons may also be used over suppose to develop continuity. So rather than using a continuous cable, you are using small for every span you are using small cable, and then you are attaching with, let's say, cap cable or a straight cable. and that's how we are maintaining the continuity of the this of the cables. So based on method of construction, continuous beams can be classified as a fully continuous beams, actually in which your actually tendons are generally continuous from one end to other end. There is no disconnection. And in the case of partially continuous, where each span is first precast as a simple beam, and then the elements are assembled so to form the continuous member. And this continuous, how to achieve this continuity? Every single span you are making for, you are precasting it, and then you are just forming using cape cables or short tendons over the supports. So you have tendon for single span, for every single span, and at the support you are using cape cables or short tendons over the to make it a continuous member. So now it is important that you analyze the secondary moments. So to calculate the secondary moment, there are some basic assumptions already there, such as elastic behavior of materials and linear strain distribution across the section should be followed. There are some few other assumptions as well for the analysis of secondary moment. The first is the effect of change in the length of members due to pre-stressing force and external loading is generally negligible. Also, the cable friction is considered to be negligible, so that the pre-stressing force is constant at all points of the cable. So one is effect of change in the length of member is you are taking it as negligible. Also, the friction force also you are neglecting, so that precision force is constant throughout the cable, because the friction, as you go from one point to the other end, it's getting less and less and less, and the friction force become more and more, and the precision force become less and less and less. Now there are several methods of analyzing statically indeterminate pre-stress structure. Like they generally use principle like three moment theorem, consistent deformation, and tendon reaction. So now these methods are given in detail in the note I have given, so I hope you try to understand it, and if you have any problem then you ask. Okay, thank you.